Okay, now I'm on stage. Thank you very much, Alessia, for those kind words. And I'm very much delighted to be here in person and to meet all DLD friends on this great event. So it's great to be here again and meet and chat. So now, after light installations, we go to quantum technology. It's a big move, but let's see how we go through this. So the purpose of this session is to give you a short status of quantum technology, where it stands, what it is all about. And I will do this, of course, with three very senior experts on that topic, and I will introduce them in a minute. So before I do this, I will quickly frame the situation and what the situation is about quantum technology. So if we just quickly look into this, the age of quantum supremacy is approaching. And the public and private fundings are skyrocketing, and global competition is increasing with the US in the lead. You see that question mark, and that question mark is on purpose. We have only limited visibility into the data of China, so there are definitely some assumptions about what is going on there, and we will see it here. So there is a lot of movement. If we just look into patents, we see that China is leading in that space. We also see that especially public funding planned, China is basically outperforming all the other regions. So the expectation is that within the next 5 years, something will happening there. Also, what we see is that there is incredible capital moving into that space. On the left-hand side, you see single investment deals in the range of 650 million and that kind of manner. And on the other side, we see that already until today, the announced fundings for 2021 are already outperforming the total funding of 2020. So there is more to be expected. And what we also see is that most of the fundings are currently going into hardware players, and VCs are the driving engine on that respect. And also we see that North America, and especially the US, is leading here with 50% of the startups, 80% of all startup funding is going into that space. And we see also that the 10 biggest hardware players are based in North America. So lots is going there. As I mentioned before, China and Europe are trying to catch up based on the public funding planned. And we see China is really leading the pack here, and they also included quantum technology into their 5-year planning. Then, if we just look into the 3 main areas of quantum technology, so quantum communication, of course, is leading and has the largest estimated market and market dynamics and number of players. Quantum sensing and quantum communication is basically a little bit behind. Also interesting space, but in terms of the dynamics in those 2 areas, it's of course a little bit behind quantum communication. We will look into quantum communication and into quantum computing in a minute when we discuss this with our experts. So overall, we can say beside the component manufacturers, the most players are in application software, and whereas the largest deals are still in hardware. So that's a very quick overview, and now I'm very much delighted to discuss those 3 topics a little bit with my 3 guests on stage here. On one side, it's Heike Riel, IBM fellow and lead of IBM Research, Quantum Europe and Africa. Then We will have Herbert Mangesius, general partner of Vsquared Ventures. Both will be here on stage. And then we have virtually joining us Helmut Leopold, head of Center for Digital Safety and Security from the Austrian Institute of Technology. So, Heike, please come and join me on stage and tell us a little bit about the status of quantum computing.
Of course. Thank you very much for having me. It's a great pleasure to talk about quantum computing. And just quickly, what are quantum computers? I mean, we are using the laws of quantum physics for computing. We are using quantum bits instead of bits. And why are we doing this? Because quantum computers have the great potential to solve certain problems which classical computers cannot solve. There are still many problems, actually sometimes we are not aware of them, which classical computers can't solve because their complexity is increasing exponentially with the number of parameters. And even the biggest supercomputers we can build today or we will build in the future cannot solve those problems accurately. So for some of those problems, we would like to build quantum computers. And 2 years ago, or 2.5 years ago, I was actually here giving a presentation about the basics. So please go back and look at this presentation. It's still online available. But I want to give today a bit of what has happened in the last 2 years. And so in the last 2 years, a lot of things have happened in the software, in the hardware, in the entire stack of also how the software and the hardware works together. I showed you pictures at that time of our computers in the labs. They sit in the physics labs. In the 2 years now, we have transitioned those quantum computers into a data center. So we have engineered these systems, and we have built the IBM Quantum System 1, which is really now in a data center available. It's built for robustness, for stability, and for continuous commercial use. We also have worked on the hardware to increase the number of quantum bits, to increase also the complexity of problems you can solve. I have to warn you, they're still in the toy problem, so they have not met yet the quantum advantage. But we have built a roadmap that within the next 2-3 years, we want to demonstrate the quantum advantage. And for us, this means that we really provide value to a problem which is relevant for a business. So it's not just a toy problem or just an artificial problem, but a problem which helps in the business. And of course, this also has to come with the software because education is important, and not everyone is a quantum expert, but we want to use quantum computers. And so we have also built, a lot is going on in the software development. A lot of companies are also coming up, and we are building an open source software stack that people can just use Python and program quantum computers. We want to make it very frictionless for developers to use quantum computers for solving the problems. And just to finalize here, it's really an exciting time, and some of you may have seen it on the 15th of June. We have actually brought the first quantum computer, the first quantum computer from the US, the IBM System 1, to Germany. It's sitting now in Baden-Württemberg, and Fraunhofer and their partners are using the system with full data sovereignty, data staying in Europe. And it's an exciting time for all of us to be in quantum computing and in computing in general.
Absolutely. So you said, the main intention is, of course, to develop those computers for business, for solving business problems. So how much is reality on that one, or how much is still working in labs or in lab environments?
So we work on all the different ends, right? From making it easy for the people to use the computers and also for demonstrating the quantum advantage. And what we do right now is, with the hardware which is available, we are developing new algorithms dedicated to the quantum computer to solve problems which cannot be solved by classical computers. And we test those on the hardware which is available. This means on smaller toy problems. But with the increase of the hardware, we also then can use these quantum algorithms which we are developing to solve real-world problems. And with scaling up the hardware, we also can introduce an error correction. And as I said, like in the roadmap which we have, we want to really demonstrate in like 2-3 years the quantum advantage, that we can solve a business problem which a classical computer cannot solve and provide value.
So tell me a little bit about, the performance of your IBM quantum computer. We are always reading numbers of qubits are increasing, and then we had a nice, interesting discussion before we actually jumped on that stage. So tell the audience a little bit about what is this all about? Is more qubits better, or has it something to do with quality of qubits?
Yeah, so as quantum computing is a difficult topic. So if you go in all the details of comparing performance, it's can get pretty complex. So of course you try to find an easy parameter, and often just the number of qubits is used. But the number of qubits actually does not tell you anything about how complex a problem is a quantum computer can solve. Because if they are not entangled, if they are not kind of using the laws of quantum physics, then the complexity is not increasing, the problem is which they can solve. So it's a quality also which is important. The quantity, of course, is also important, but also the quality. And we also try to come up with a benchmarking number, how different quantum computers can also be compared with, and we call it quantum volume. And so in this quantum volume, all these different parameters which influence the complexity of the problem you can solve with a quantum computer is kind of combined. And this is the number of qubits, but it's in particular also the quality of the qubits, the fidelity, this means the error which the qubits may have, the noise, the number of gates you can use, the entanglement of the system. So there is a lot of different parameters which actually go into this number of quantum volume. And of course, the larger the quantum volume, the more you can do with it.
Thank you, Heike, for those very interesting insights into quantum computing. And now we will switch the perspective into quantum communication. And now we should have Helmut Leopold on screen joining us.
Hello.
Helmut, great to have you. So just give us your perspective on quantum communication. Where is that going?
Thank you very much for inviting me. And just to briefly summarize a very complex technology in a few minutes, which will end up that at the moment, I think from the three areas, quantum computing, quantum sensing, and quantum communication, I think the third part is has reached the highest matureness level. In a nutshell, you can buy already now commercial products which are working. So the industry is currently able to use this strange quantum effect, where not everybody understands. I would say the scientists even don't yet know how it really works, but we can do it, we can replicate it, you can buy commercial products. So we have achieved a very high matureness level now. With this system, we can now generate on large distance even random numbers, which is used now for the first application for generating keys for encryption applications, which is guaranteed, so we can prove it by physical means, by mathematical means, we can prove it that no computer, even not the most fancy quantum computer, which will be developed once in the future, can crack these keys which are used for encryption. So we have the highest level of key generation achieved. On a program level, the community has to know, in the meantime, such a lot of dynamics went on. So we have now in Europe a big program called EuroQCI, Euro Quantum Communication Infrastructure, which is a 10 years program. It's not a research program as such, but it's a program to bring the infrastructure into real life within the next 10 years. Basically on satellites for large distances, and also on fiber infrastructure for closer campus and city networks. So that's a program where the European Commission, the member states have already made their commitments. The industry is part of it. So we have commercial products, and so far everything is fine. But here I would like to point at two important aspects. The whole conference is about innovation, and the first learning is having lab results, having implemented high tech is not yet really innovation. So science is not, it's a starting point, but it's not innovation. For creating impacts in the market, we have more or less two important issues, and for Europe now, very essential issues. First, we have to have an ecosystem of experts which are able to build, operate, maintain, and also use the new technology. And here we are definitely behind the Chinese development. So already 10 years ago, China had a similar activity. Right now, what we are doing right now, we have already now 10 years of experience in operating a very complex technology. So we need engineers, we need applications which are using this new technology. This has to be built, this has to be created. And that's also an important part of this program, to build up this ecosystem of experts and, from an industry perspective, manufacturers which are able to build the systems. So I mentioned before that we can buy already commercially those systems, but for the moment, from a European perspective point of view, the manufacturers, all of them are from Asia. So if we want to implement a highly secure infrastructure, even for transferring classified information in Europe on a governmental context, for example, there is the need that we also have trusted European manufacturers, which are not yet there. So in a nutshell, this Euro QCI program currently, research was done the last 20 years. It's now a security program. How do we use more and in which applications higher levels of security and using encryption on a much wider extent? An industry program, developing suppliers and manufacturers and system integrators and operators in Europe, which are able to manage this. And then also, of course, applications, because now we have keys, we have high tech, like a telecom equipment, but it has to be used on the application side by different applications for encrypting at the end, video, voice, data, and so on. And this has to be built. And this takes money, this takes time, and this needs also a lot of engineers' knowledge, which we have to develop. So the most important summary, I would say, it's not done when we spend billions of money in basic science and in lab developments. At the end, we have also to build a framework that technology is used and brought into practice somehow, and market at the end can work. We need the experts and we need the stakeholders and actors.
Helmut, thank you very much. And I think you are touching a very important point, from invention and research to industrialization. And if you compare the European situation with what is going on in China, for example, do you think we are ahead or we are behind?
The funny thing is, and I think that's the situation of Europe, I know definitely, and I think the rest of the world also recognized it, the whole knowledge, science, is coming from Europe. It was everything developed. Everything what China developed on their industrial side came from Europe, from the different universities, research centers. So we developed it. We had the know-how here. But of course, the next step, having a vision and implementing the technology, even that's a little the problem with this technology. Of course, when we have just a commercial business case discussion, it's a little bit too early, the market is not yet there, governmental customers are not yet prepared to implement these things. So it's a tricky situation. That was then the effect that China made now this big step in implementing technology. You are creating the patents, you're creating applications, you get experience. And here, for the moment, they are very much ahead of us because they have experience in using technology, which stimulates a lot of other aspects. If you have thousands of engineers which know the technology, other side effects which will also happen. And here I would like to add one more point. What will be next step or what comes after this encryption application? Here we are in the world of photonics. That's a little bit different to the quantum computing world. We are using very low energy, highly integrated with currently the R&D community is working on bringing everything on a chip level so it will become cheap and all this stuff. But here we also develop a photonics industry, a know-how on photonics. And I think using this optical technology for the moment in the communication world, but also then for computation, for computing and switching and all these applications. This will be here a real game changer, I think, in the future, because we will increase the efforts for the communication in the world, and we need a new technology. And just staying on the electronics as it is at the moment, I think there will be an end, and this will be so the photonics world after this in combination with this quantum world will be a very essential future industrial direction.
One other topic related to quantum communication is everything about cryptography, and many companies which are storing huge amount of data for a long period of time, they are getting a little bit afraid of what is going on in the quantum technology space. How important is post-quantum cryptography?
So that's why you're asking more or less the motivation why we're doing it. So the big threat, what we have currently in all for our applications for the asymmetric encryption world, is that here we are working with keys, with public keys and private keys which are generated by specific means. And the big threat is if a quantum computer reaches a specific computing power, by knowing the public key, for example, as a private public key encryption scheme, the public key is known, which is known by everybody, and you have a quantum computer, then you can calculate the private key. So everything which is now encrypted by a traditional state-of-the-art today's public-private key scheme can potentially be tomorrow decrypted by somebody which has invested in a powerful quantum computer and can read your data. And the only means of fighting against this, or be protected against this potential threat, is building the next level of key generation, so building keys which cannot be calculated by any kind of computer. And that's the quantum key distribution technology on one hand, or post-quantum encryption on the other hand, which solves this problem at the end. So I think when we, on a risk-based assumption discussion, when we take this risk serious, that sometimes in the next years, when we're talking about centuries, a quantum computer will be available and can calculate and corrupt more or less our public-private key encryption, the asymmetric encryption schemes, then we have to change our technology and we have to build on a new technology, and that's quantum encryption.
Yeah. Helmut, many thanks for this insightful perspective. Thank you very much to Vienna. Thank you.
Thank you, Jimmy.
So now we will shift our perspective into the investor space. And Herbert, why not joining me on stage? Herbert Mangesius from Vsquared Ventures, and Herbert will tell us a little bit about the perspective from the investors.
Thank you. Thanks for being here. I think it's important to understand for an investor, especially venture capital investor, that our business is the business of big gains, and obtaining big gains requires risk, big risks. And for us in particular, the big risks are mostly technology risks. So we embrace technology, and we often, and in the case of quantum computing, we kind of require a breakthrough, a technological breakthrough, in order for this market to prosper, to evolve. The previous speaker mentioned it, the market isn't there, everybody's waiting for the market, nobody wants to invest in technology breakthroughs, and this is something where we get into the game. So for us, we embrace technology to the level that the science is secured, so there are no big open scientific questions, and it's mostly about technology development and process, know-how development, integration development, all these aspects the previous speaker Helmut has mentioned, which is something that has been done to a tremendous extent in China, but also in the United States, as we heard from IBM, for example, and this is something we are lacking. So for us, it is about figuring out where the few teams, the very, very few people in Europe are that have this capability, and finance them and work together with them in order to accumulate know-how, talent to a sufficient size, and together create the market. So it's a very different role from classical venture capital, which is also into risks, but there you have much more competition. It's much less competition here, sometimes just 1, 2, or 3 teams at most in Europe. And from there, we work with corporate partners, with political partners, and it's really a role of fostering and creating market structures. So that's what we do.
Okay, that's a great perspective from the investors, yeah. And you know, looking into the future, we saw the figure with you know, application software and hardware. So large investments are going into hardware. Many investments are going into application software. So what is the sweet spot for future investments?
Okay, so we chose
Everybody wants to invest here.
Okay, so we chose hardware because we believe it's the time for hardware, and these technologies, they need to mature in order to have this breakthrough. So I think most of the pure software players, and I completely understand it because classical VC thinks of software as the scalable thing, and hardware doesn't scale. So we throw our money into software if we have some plausible story that this can eventually become something big. But we believe now is really the time of hardware, and it's rather a co-development of hardware and software. And like the image that I often have in mind is an hourglass. So you come from the maybe corporate world with all of these applications and problems, and you need to nail it down. And from the hardware side, you come as well building physical qubits into a substrate, into computer, electronic infrastructure, integration into high-performance computing systems, etc. And somewhere in the middle, there's a very thin place where the application side needs to meet the hardware development side. And in our view, this is really a task. So the prime task today is find an application that has some business value, as was pointed out, and solve it as good as possible to get to this quantum advantage. So we trade performance over universality for now in order to demonstrate that quantum computers can reach this business advantage. So solving a meaningful problem better than any digital computer we have today. So I think it's a combination of software and hardware, and it's rather for Europe because we do not have these budgets as we have in China or the United States to figure out cooperation models with companies, big companies, which have meaningful problems, maybe software players who innovate on the methodological side, algorithmic side, and map these onto architectures and quantum computing circuit designs eventually. And to bring all of these together needs one big player that understands everything and can integrate it somehow. And it needs, of course, the corporate side with the meaningful problems, them having skin in the game and learning by doing stuff and not putting efforts and money into research and reading about what happens in the world. It's really about jointly working together and learning while we walk basically the way. That's what needs to be done. And there I see in these ecosystems and cooperation models very good opportunities to invest both hardware component, maybe also software side, but it needs to be integrative.
You guys were one of the first investors into IQM. So what made you choose this target?
So as I mentioned, IQM in Finland, at Aalto University, is a very special case because it was untapped. There was a huge expertise on the hardware side, a huge scientific expertise, young people, which were available at a sufficient size, team-wise and complexity-wise. So there were very different topics covered. And for us, there was no place as that where you had a full team and this full capability, access to equipment, to clean room environments, to set up such a company, an independent company. So that's why we chose this, plus their approach to collaborate, which is a European capability, I think, and build QASIC, so application-specific circuits, so being with the algorithm that solves a problem very, very close to the physics in order to achieve first quantum advantage, which is different from many other approaches that are known.
Herbert, thank you very much for your perspective. So that's the end of this session. So thank you for joining us, for listening. And all the data and figures will be launched in our Quantum Technology Monitor, which will be published next week. So watch out for this, and you will find more data and figures in that Quantum Technology Monitor. Thank you very much.